Seems like I'm live on YouTube and I am live on Twitch. Let's check. Uh, yep, I am live on Twitch and on YouTube. Yep, I'm live on YouTube too. Okay, yesterday I messed up. I didn't complete the questions, and that is very embarrassing. But today I will complete these two are the only questions. Question number 9 and 10 that are remaining. And after completing these, we will move on with the next chapter, chapter number 5. So, first item, yep, David Goggins. He's always there. And I'll go with my folder. Um, yep, yep, this is the file I was working with. Now, yep, let's start doing this from the start. Assume that we did part A and we did part B, but we have to move on to C and D. But let's revise what we did in part A and in part B. Assume that the zeroth register holds the least significant 64 bits of a 128-bit integer. So the thing is basically that the zeroth register, this holds least significant 64 bits of a 128-bit number, and the x1 register holds the MSB for the same number, and there is another 128-bit number whose LSB is in the second register and whose MSB is in the third register. And yep, first for the first part, we wrote these two lines to compare the contents of these two registers and right conditionally compare, and the condition would be equal. Okay, so this thing first compares the MSB that is in the first and in the third register, and then it conditionally compares the LSBs. That is, if the MSBs are equal, only then it compares the LSBs, and if it is not equal, then the P state is not updated and it is still in the not equal state, and that is what we want. We want to update the P state flags for being equal or not equal. Then we wrote a thing to to left shift the number A that is in the zeroth and the first register, and then store the result in the B register. So first, we just normally left shift the LSB and MSB and save them into the other into the second and third registers, which store the other number. And then now we have to get the MSB of the LSB, that is the MSB of the third register, and add that to the LSB. Add that to the LSB of the MSB, right? LSB of the MSB. So this thing gets the unsigned binary, unsigned bit fitting extended. Uh, it gets the IFO. So what this command does is it takes the value in the zeroth register, and starting at the 63rd position, it gets 1 byte from there and stores that into the fourth register. So this gets the MSB of the zeroth register, and then we add the MSB to the contents of the third register, uh, which hold the MSB, left shifted MSB. Now, moving on to part 3. For part 3, we have to add B to A, right? We have to add B to A. So for that, we can, yeah, that would be simple. First, we will add the LSBs, that is the content of the zeroth register and the contents of the second register. Oh shit, my, yep. And let's say we will use the fourth and the fifth register to store the added sum. So for that, we have add and store in the fourth register the sum of the zeroth and the first register. And then we have to add and store in the fifth register the sum of the MS, my bad, my actual bad, the sum of the MSBs, which is the first and the third register. And now we want to see if there is a carry in this part. And if there is, then we want to increase the MSB by 1. So first we should add the MSB and then we should add the LSB. So the P state register is uh, the P state uh, flag is whatever is this, whatever this means, the addition of the LSB put it to. And now we have to check if there is a carry and conditionally increase the contents of the fifth register. Right, conditionally increase the contents of the fifth register. And what is the condition that I want? Conditionally increase, conditional increment, mm, conditional increment, and conditional increment. This is the thing for conditional increment. Yep. Um, Increment the contents of the fifth register. And the condition I want to check for um, i- is carryover. How to check for carryover? And there was a table here. Yep, this is it. Higher and high greater than equal to unsigned signed overflow. Yes, I want to check for overflow. Carry set unsigned overflow is equal to 1 CS carry set. No unsigned overflow. Nope. Signed overflow VS. No signed overflow. Well, the numbers that we are using are they signed or unsigned? Well, we can treat them, I think, as signed and check for signed overflow. And if there is a overflow, then signed overflow is VS. VS. If there is no overflow, then I increase the contents of the fifth register. That makes sense, actually. Now let me ask ChatGPT if the answer is correct. Add A to B. Okay, this is my answer. Okay, let me give the whole thing that I have written. And this is the question. I will just copy and paste it. Below is my answer for the above question. Is it correct? Let's see, your solution is close. That is what you say all the time. But there is a small issue. Let's analyze your approach carefully, understanding the problem. And use the reasoning part. You give two 128-bit numbers. A is in the zeroth and the first register, and B is in the third and second register. Okay. You need to add compute A plus B. Okay, which means add the lower 64 bits. I am stupid. Am I stupid? Nope, I'm not stupid. And add the upper 64 bits. First plus 3. Okay. Including any carry from the lower addition. Analyzing your code. Well, you are messing up. ChatGPT, let us use. Well, we can actually use DeepSeek. DeepSeek. Okay. You have to verify if I am a human or not. That would be funny if I failed this test. It would actually be funny if I failed it. Right. Yes, my camera is still working. Okay. No, don't search. Use a DeepThink R1 model. Yeah, it is thinking. Okay, let's see. Now, first, when adding 128-bit numbers, you need to add the lower parts first, which can set the carry if there is an overflow. Then you can add the higher parts along with the carry. The usual approach is adds 0 to which sets flag, then uh, uh, adds which adds with carry. That way, the carry from the addition is included in the higher part. Looking at the users, and they do add this is and then add this is then increase. Let's break it down. After adds this the carry C is set if there was an overflow. Then they add this or normally which doesn't account for the carry. Then C increase this VS this is the overflow condition which checks if the V is set, but in addition the overflow bit isn't the same as the carry bit. Okay, for unsigned addition the carry flag is what's important. So carry is different from overflow. I am stupid. Okay, so maybe using CS carry set instead of VS here. Okay, but even then, see, increase will increment X5 if VS is true. However, when you add the high parts, you should add the carry from the previous addition. The standard way is to use and see add with carry, which automatically adds the carry. So instead of adding followed by add followed by conditional increase, add with carry would handle it. So the correct sequence would be adds x4 uh, 0 and 2 followed by add with carry. That way the higher parts the higher part is x1 plus x3 plus carry, where C is the carry from the lower base. The user's code does adds then a regular add and then CS will be. That seems incorrect because VS checks for signed overflow, not for carry. So if the low addition overflows carries it, the high parts need to add one. But using conditional increase with VS overflow might not capture that. Also, after adds, the carry is in the C flag, not V. So conditional increase should use CS, not VS. That makes sense, but even then, using add conditional is more straightforward. That actually makes sense. So, uh, saying that this will make more sense. Wait, I messed up. This should be 5. Wait, I am using 5 to store the LSB. No, 5 to store the MSB. Okay, I will add the MSB later. First, I will add the LSB. Uh, okay, this seems correct, very correct. Yep, yep, that is correct. First, I add the LSB, which is in the zeroth and the second register, and store that into the fourth register. And since I'm using adds s, this will also update the conditional flags. Then I will add the content of the first and the third register, which is stored the MSB, and save that into the fifth, and also add the carry if there is a carry in the flag, if there is a carry flag in the P state register, and also update the P state register if there is a carry because of the addition of these two values. Okay, now subtract B from A. Subtract B from A. Well, for subtraction, I should first subtract the. Where do we begin subtracting? Subtracting from first we subtract the LSB and see if there is a um, carry, negative carry, or what you call it in subtraction, negative something, subs, store it in the fourth register, subtract. I have to uh, subtract B from A, from A. So A is in the zeroth register, and then choose CS, maybe sucks for, I think this might be an instruction. And what I'm trying to do here is first subtract from the zeroth register the contents of the second register, which store the LSBs of A and B respectively, and store that into the fourth register. So this might mean two things, that the value in the zeroth register was bigger than the value in the second register, which would mean okay, we have no underflow. But if the val the LS this zeroth register is smaller than the second register, then we will have an underflow. That is, bad things would happen, right? We would get a negative number. Yes, we would actually get a negative number, which is not good. Yeah, which is not good. And then I want to subtract from the first register, that is the MSB of A, the MSB of B, which is in the third register, and store it into the fifth register and conditionally subtract 1 because of this C. I think this should work. Let's see. Yo, ChatGPT is not working, but DeepSeek is working. Go China, I guess. I mean, is the below code correct, or the above question? Let's see, the user is asking if their code for subtract B from A using 128-bit integer is correct. Their code is this. Wait, first I need to recall how 128-bit subtraction works in ARM assembly. For addition, we use adds and ADCS, right? So for subtracting, it should be similar with subtraction instruction. Yeah, right? Yep. The user is using subs for the lower 64 bits. That makes sense because subtraction subtracts and sets the flag. Subs, yes, including the carry flag, which actually represents the borrow in the borrow, not underflow. It is called borrow in subtraction. Then the upper bits, they have sucks. But I don't remember an instruction called sucks in ARM. Oh, maybe they meant SBCS subs, which is subtract with carry, because in subtraction the carry flag is inverted for borrow. So SBCS would subtract the upper bits along with the borrow from the lower subtraction. That makes sense. So the correct instruction should be is subs for the lower part, the SBCS for the upper part. Okay, the user wrote sucks, which is probably a typo. Also, the order of the registers matter in subtraction. It's in destination equal to first operand minus the second operand minus borrow. So the upper part it's x1 a higher minus x3 a lower minus b high is minus the borrow, which is 1 minus carry because carry is inverted in subtraction. Okay, so if I have a borrow, then this would become what? 0. And if it is 0, then I will minus 1. But if it is 1, then I will minus nothing. Okay. Another thing, the user is storing the result in x4 and x5 if the requirement is to update a in place. Since the original question was adding to a, maybe the result should be stored back into x0 and x1, but the question says this subtract b from a, so likely the result should be stored in x0 and x1. However, the user's code uses x4 and x5 unless they need to prevent the original a to preserve the original a, but the problem statement doesn't specify that, so maybe that's an issue too. Also, the original code for addition used adds correctly, but here six is incorrect, so the correct sequence should be subs this and SVCS this. That actually makes sense. So what there's what it is saying there is shit. So what it is saying is this. It is not sucks, it is subs. That is now my code is correct. Subs is the contents of 0 and second register, and then subs subs the contents of first and the third register. Yep, subs or something. Okay. And this is storing it in the zeroth and the first register, that is the original place where the A number is stored. But I want to store them in the fourth and the fifth register. Is correct. Now we are done with question number 9. Now moving on to question number 10. The C standard library provides the OpenNAT this function, which is documented in section 2 of the Linux manual pages. This function is a very small wrapper to allow C programs to access the OpenNAT system call. Okay, assembly programmers can access the system call directly in ARM64 Linux. The system call number for OpenNAT is 56. The Linux system calls can be found on a Linux system uh, in user include ASM generic unnested unistandard.h. Write the ARM64 assembly instructions and directives necessary to make a Linux system call to open a file named input.txt for reading without using the C standard library. In other words, write the assembly equivalent to open at minus input.txt read only using the svc instruction. Okay, now we want to write. Okay, we got this. Okay, I don't know. I have literally no idea what we are supposed to do, but uh, we'll first write the things that you are supposed to write, define the main function, and then, okay, I don't know how will I get an file object inside. Let's first create a file, and there will be hello world in that, and let's store it into text.txt at text.txt hello world. Okay, I have a file named text.txt which contains hello world, and now I want to read that file in assembly using a system call. So I literally have no idea. So what we can do is write a C program that does it for us. Um, read.c. Yes, first we can write a C program which does that, and then we can see the assembly for that program. Include and mind main. Inside, I want to use what is the function that it used. It used open at this open at and this thing use of undeclared variable read only minus 100 RD only. So do I have to provide it as a string? Call undeclared function this ISO and call later accordingly. Okay, I want to read using a system call. Okay, ARM64 Mac OS ARM64 is called table in ARM64 Mac OS 6 syscalls. Yeah, let's see. The page is not found here. I want to see the syscall number for read. Mm, So this person seems to be writing assembly code inside of C. That is cool, I guess. Mm, Kernel syscalls, the Apple wiki. Kernel syscall Mach. What is Mach? AR64 R64 syscall table. Chromium OS talks. ARM64-bit, and for read, I want to see what is the syscall for read. Read is this 63. No, it is 3F. And what do I have to provide? 3F, 3F. What do I have to provide? First argument, second, third, fourth, fifth. Okay. Uh, Here, yes. Unsigned it FD. Then character buffer, then size count, how much I want to read. That makes sense. And character buffer, that is a pointer. Okay, unsigned int FD. What is this unsigned int FD? Hmm, 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 hmm. What is unsigned int FD? When I want to write in that, okay. For stand, okay, I have to provide in there. Hmm. When I want to write at the place of this, the second argument, I provide a character buffer which has the address for the string that I want to print, and then there is the amount of characters that I want to print. And the first register, that is the 0th register, contains the address, contains a number which would tell where I want to write. And 1 means standard output. So now I want to read, but I want to read a file. How can I read a file? Chat GPT, or yeah, Chat GPT is okay. Okay, what is the what is it called? Unsigned int fd, the int fd in AArch64 is called for read, to read from a file. In AArch64, when making a syscall to read from a file syscall, the first argument is an unsigned in file descriptor. Understanding unsigned int fd file descriptor in AArch64 read syscall, the file descriptor. 0 file contains the file descriptor. X1 pointed to the buffer where the data will be stored, and the number of bytes that I want to read. The syscall number read in AArch64 is 63. It's 63. Well, it is 63. And then um, open the file, sys open at get fd, then read from the file, then choose the file, then close the file. ARM64 assembly example reading 100 bytes from fd equal 3. Okay, move 63 into the 8th register, which is the syscall number, into the 8th register, but I will be moving it to the 16th register. And then I want to move the number 3 to the 0th register, the address of the buffer where I want to store the data of the file, and then the number of bytes that I want to read, and then I do the syscall. The file descriptor, 0 is a standard in, 1 is a standard out, 2 is a standard error. If you open a file using sysop, then you will receive a new file descriptor example. This which you can use in read. Wait, so I have to use 3, and I can just leave this one. Okay, first, how many bytes do I want to read? Let's say I have a label called file which stores bytes, 100 bytes. How can I store 100 bytes? Hmm. What is the directive? To skip 100 bytes in ARch64. Instruction for 1 byte non-zero extend. Guide to ARM64 assembly next. LDR, nope, nope, nope. In the data section of my program, I want to have a label which points to a 100 byte 100 byte memory. How can I, which directive can I use to, I think it is something like skip or something I can use to get a 100 bytes of space. Is it like dot skip? Yep, dot skip or dot space. Dot skip is preferred. Section BSS align for buffer dot skip 100. Skip 100 bytes. That is okay. Makes sense. Dot skip 100 bytes. Now, my file label points to a memory location, points to the first byte, which have 100 byte, 99 bytes after it, which are free to use. Now, let me load in the zeroth register. Zero moves in the zeroth register. What? 3. 3 is a file is the file descriptor which tells the read syscall that I want to read a file, and now I want to get the address which this label file contains in the first register to give it to the syscall. For that, I will get the page address and store it in the first register, the page address for file, and now I will add the offset to the first register for the file label. And then in the third register, I want to tell how many number of bytes I want to read. And I want to read 100 bytes. That's it. Now, yes, the syscall number. I move the syscall number into the 16th register. The syscall number is 63. And then I call the syscall. And then I return this. Is that it? That's all I want to do. Then I just return. Let me print. After this, I should have. Let's see if this compiles. Clang. Oh, yeah, well, it does actually compile. Invalid syscall dot out. Okay, invalid syscall. How do I tell it that I want to read? What is the name of the file that I want to read from? That makes sense. How do I tell it the name of the file that I want to read from? File descriptor 3. Invoke syscall. Okay. In this, in this, how do I tell the syscall the name of the file want to read? Yes, tell this called the name of the file you want to read. You must first open the file using the openat syscall, which takes a file name as an argument. The kernel returns a file descriptor ft, which you can then pass to the sysread call to read. Okay, openat this openat first int file and then file name int flags user mode. Okay, and open at, and there must be something like close at or something. Open, okay, close. This will just close it. Okay, this I guess makes a little sense. To open the file, pass the name as a pointer in the uh, first register. The kernel returns a file descriptor in zeroth, and then I can pass that file descriptor into the zeroth to the first register. Okay. Close and sign it. File descriptor. Okay. File and file name is an ASCII, which stores the file name text.txt. This is the name of the file. Now, first, before anything else, I want to call the openat syscall, which will give me a file descriptor. For that, I want to move, let's say, into the zeroth register, value 0, and into the first register I want to get the address of the name of the file. Okay, so ADRP, first I get the page address of file name here, and then add the offset to it like this. page offset. Okay, now do I have everything? Nope. I have to store in the 16th register the number of the syscall, which is 56. 56. And then I can just call the syscall. Okay, after calling this in the 0th register, I should have a file descriptor which I want to pass on. The file descriptor which I want to pass on to the 0th register. Well, the 0th register already has it. Okay. Mm, So after making the first syscall to get to open the file, okay, I will, okay. So and this part of the code opens the file and stores in the 0th register a file descriptor. And now I want to make a syscall to actually read the file. And for that, in the 0th register, I already have the file descriptor. And in the first register, I get the address of the file, the address of the place where I want to store the file. And then in the third register, I tell the amount of bytes that I want to read. And then I make the syscall. So this much should compile. Okay, it does compile, and there is an invalid syscall, and I don't know which one it is. Okay, which syscall is invalid? Is it this? Let's see which syscall is invalid. Okay, the second syscall is invalid. This second syscall seems to be invalid somehow. Okay, 63 is the number for reading, right? 63 is to read, and in the 0th register, I have the file descriptor which I got from openit instruction, and then mm, yep, in the first register I have the place, the address where I want to store, and then I give the size, that is 100 bytes. I want to read 100 bytes. Let's maybe this. Oh, I am stupid. This has to in the second register, not the 100, not the third register. Now I should not get any error. I got an error in chapter. Let's say maybe the number of bytes are messing up, or maybe I don't have enough characters in the file that I'm reading. I'm saying that I want to read 100 bytes, but I don't have a 100 byte long file. After writing a lot of things here, I should actually have a 100 bytes here. I don't know currently how long the file is, but after completing this sentence, I should have a 100 bytes long file. I hope. Okay. Biden. Biden. Okay. Let's see. Okay, it's still invalid. Nope. 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 Chapter 4. Okay. I am getting 100 bytes here. Why is this invalid? In the 0th register, I have the file descriptor. After making this call, I have the file descriptor in the 0th register. And in the first, I have the address to the place where I want to store the file. In the second, I have the number of bytes that I want to read. And then in the 16th register, I have the syscall number, which is 63. And then I am making this call with all the arguments, proper arguments. Is it because I'm not closing the file? 57? Wait, I should maybe store the file descriptor in another register onto the stack maybe. Yes, so that I can use it later to close the file. Okay, store the contents of the zeroth register onto the stack, and I want to have like how many bytes? 8 bytes of storage on the stack. And then after this, I want to get it back, the file descriptor. So um, load in the zeroth register what I stored in the stack, and then get the original value of the stack. That makes sense. And now, after getting the file descriptor in the zeroth register, I want to move in the 16th register the syscall for close the number of the number 57, which represents the closest call, and then make the closest call lang, and then invalid syscall. Okay, where am I messing up? I am doing this right, it seems. Okay, getting the place, the address where I want to store the contents of the file, specifying how many bytes I want to read, and then giving the syscall number to read, and then calling the syscall, telling the operating system that I want to read this. And I even have in the zeroth register the file descriptor for the file. Hmm. What did ChatGPT say before? AArch64 example. Test.txt, that is the file name. And then they have a buffer here. Okay, global start. It moves 56 in the 8th register, and then moves use the current directory means 100. Okay, so okay, instead of 0 there has to be 100 here. Is that correct? Still incorrect. Is it because of the last this? Let's see. Let's incorrect. Okay. uh okay, in the zeroth register I use -100 to tell that I want to use the current directory. Then a 5 in the first register I get the pointer to the file name, and then in the second and third register I have to give 00. Okay, in the second and third register I have to give 00. Move in the second register 0, and move in the third register 0. And yes, this is called for closing the value, for closing the file. Invalid. Okay, I do this so that I have check if open at field negative. Okay, branch link and test. If failed, then exit. If I have 0 in the zeroth register, then my thing failed. It didn't work. And if it did, if I need in the 19th register for later use, read file. Okay, for read file, call number is 63. I store it in the 8th register. Then I move in the zeroth register the value is Okay, and then in the first I have the buffer, then in the second register I tell the number of bytes I want to read, and then I make this syscall, then I close the file by making this syscall. Okay, instead of doing this, I can simply do move into the 19th register, which won't be overwritten by making the syscalls like this, and then move into the 0th register the contents of the 19th register, and in the first register I get the address, in the second I get this. Now I want to do an exit label which will just return move in the 0th register the value what 100. I will exit the exit code 100, and after reading the file I want to see if it worked or not. So therefore I compare the contents of the 0th register with the number 0 and branch link test. And test is if they are equal. And just do that. Branch link equal. If they are equal, then I want to go to exit. Otherwise not. Now let's see. Okay, that does not seem to be a thing. And I think this should do it. Yep. Invalid syscall system call. Okay. What is the invalid syscall? Which syscall is invalid? Let's see. This, after this comparison. Now, if I don't get any error here, then that means the error is in these statements, which I am deleting here. Let's see if I get some error or not. No error. Therefore, the error is in the statements that I just deleted. In these statements, the error is here. Now, is the error in this? Let's see. Not closing the file. Nope. The error is in the read statement. Okay, the error is here in making this syscall. This has the error somehow. 63 is the number for that. Yep. Let's use the 8th register. I don't know, maybe I shouldn't do that. I've been using the 16th register to get the syscall number till now. Let's see. Okay, invalid syscall is still. Okay, let's ask ChatGPT what the heck is wrong with this. I don't think for me, and first we are getting the file descriptor here. Let's exit with the file descriptor. Okay. Instead of exiting when it is equal, let's exit with the file descriptor. And why is this happening? Am I not doing this? Is this I want to return after. Okay, it is because of this. I changed this is called register to 16 and to 8, but it should be 16. I don't know why, but it has to be 16 on Mac. Okay, and now to see the exit code, this 14 is the file descriptor. If I do it, wait, out and then echo. Okay, 14 seems to be the file descriptor every time. If I change the name of the file, what will happen then? If I delete the file, what will happen? Right, the file descriptor is same, even though I removed in the file text.txt. Still, I get the same file descriptor. And what should be the name of the file? Test.txt. That is the way I have provided the name of the file. You know, the file, even though the file does not exist right now, I am getting an error. No, the function is working properly, even though the file does not exist. That is crazy. Let's say test.txt. I'm using as keys. Yes, as keys. I should use as keys there. Now if I clang it and see the output and then see the file descriptor, it is still 14. So if I use the file descriptor 14 manually, what will happen then? I can return here to this and do this and branch when they are equal, and here for my purposes I can do the return here. And then clang it and then do the out and then see the exit code, which is 1414 is the file descriptor. Why is it still 14? What is the file descriptor? Open at this, giving -100 in the 0th register. What does it do? At this open in the current directory, it specifies that the text file is in the current directory. Then in the first register, we give the pointer to the name of the file, and in the second we give 0, which means open for reading only and not needed for read only mode. So we don't have to do anything with the third register. This is called returns a file descriptor FD in the 0th register. Okay. Now we want to call the read syscall with the file descriptor, the buffer where we want to store the data, and the number of bytes that we want to store. So 0 FD from the open at instruction. Okay, that makes sense. And then in the first register, we give the buffer where we want to store it, where we want to give the pointer to the allocated memory, and in the second register we give the number of bytes that we want to read. And now we close the file when done, and then exit the program. What happens when you run this? Okay, what does the FD syscall do? Does it what does the FD syscall do? And does it bring the file mentioned into the RAM from the hard disk into the primary storage from the secondary storage? Is that what it does? The FD is no, like OpenAT. I wanted to use the OpenAT. Does not bring a file from the secondary storage disk into the primary storage RAM. Instead, it is just a numeric handle that represents an open file inside the kernel. However, syscalls like read do bring data into the RAM by reading the file descriptor. Okay, understanding what a file descriptor is. When you open a file using OpenAT, the kernel returns a file descriptor. The file descriptor is just a reference number this that points to an entry in the kernel's file table. It allows the process to interact with the file, read, write, etc., without needing to know its disk location. How does data move? OpenAT does not move data into the RAM. It just creates a reference file descriptor. Read moves data into the RAM. It loads file contents from disk secondary storage into a buffer. In primary storage, RAM, step data movement. Open, no data movement yet. When I do call the 56th syscall, which is OpenAT, I get a file descriptor. No file content is loaded into the RAM yet because I have not provided any address to store the data of the file, right? But I provide the address when I am doing the reading here in the first register, the address of the buffer. Read data from file, brings data into the RAM. The kernel reads from disk and copies data into buffer in RAM. Okay, now the file data is in primary storage. Choose file. FD is freed, but data stays in RAM when I close the file. Okay, the file descriptor is released. The file contents stay in RAM inside buffer. Does read always read from disk? Not always. If the file is recently accessed Linux, we cache it in RAM. If cached, read just copies from memory instead of disk. This is much faster. This caching is done by the page cache in the kernel. Open it. Opens a file and gives FD, but does not load data into the RAM. Okay, so the open at command gives a kind of token and gives a sort of pointer which a sort of key w- whose value is the file we can after after getting the file descriptor we can use it to refer to the file in the disk without actually specifying its physical address. I guess that is what it means. Without actually specifying the physical address of the file that you want to read, we can use a file descriptor. And at a time, the kernel has a table which contains key value pairs which point to files which key value pairs where keys are FDs, um, uh, file descriptors, and the values are the actual location of the files. That is what it means to open a file. And the contents of the file are loaded into the RAM only when actually we call the read syscall to read the contents, and the contents are stored in the buffer provided by the programmer. And then when we close the file, we just we just remove the file descriptor from the from the file descriptor table. Is that correct? Let's see if that is correct. Oh, yeah, I have to responsive. This one seems better, just somehow better. Well, this one has this beautiful PostgreSQL example. Let's see. Yes, you have understood it perfectly. Here is a breakdown of your explanation with some refinement. Yes, you have got the right understanding. Let's break it down step by step with a few refinements. OpenAT gives a file descriptor. The file descriptor acts as a key, a short integer that refers to the file. You don't need to know the physical address of the file on disk. Instead, the kernel maintains a table, file descriptor table, that maps FDs to actual file locations. The kernel maintains a file descriptor table. Each process has its own file descriptor table. The key equal file descriptor, okay, and the value equal files metadata, including its location on disk. File descriptor, and this file descriptor points to this address, to this file, and this. That makes sense. The file is not loaded into the RAM immediately. Just opening the file, just opening the file, OpenAT does not load its content into the memory. Only metadata about the file is stored in the table. Metadata. Okay, calling read moves data into RAM. Read with file descriptor, with buffer, with size, tells the kernel find the file location using FD, read size bytes from the disk if not already cached, copy the data into the buffer which the programmer provides in RAM. When calling close removes the FD from the table, the kernel removes the FD entry from the processes table. The file descriptor itself remains on disk, but you can't access it using the FD. The file itself remains on the disk, but you can't access it using that FD anymore. Opening a file, move the 56 syscall number, that is for open at. What is open at? Like open, but at, I don't know. At is p might be a table. Okay, then minus 100 means the current directory, and then load. I want to load the file name. This is the file name that I want to get, and then 0 for read only, and I don't have to do anything with this. Now, this call 0, which is for kernel. Now is x0 now holds the file descriptor result. The kernel assigns an file descriptor example 3. It updates the processor's file descriptor table. Okay, now then I want to read the file. Move into the syscall for read, that is 63 syscall number in the 8th register, and then the file descriptor given to me, which is for example 3, which I got from the openat instruction, and move it into the 0th register. Then in the first register, I give the address for the buffer, and in the second register, I give the number of bytes that I want to call, that I want to read from the file. And then do this is called with the 0 number. 0 means I want the kernel to do this thing. The kernel if looks up the file which has the file descriptor 3 in this example. It reads 100 bytes from the file and copies them into the buffer in RAM, closing the file. When we do this, close the file, which is syscall number 57, and moves 3, which is the file descriptor, which tells that this is the file that we want to close. The kernel removes fd equals 3 from the table. The file itself is still on the disk, but the process can't access it anymore using fd equals 3. OpenAT creates an FD but does not load data. Kernel maintains a file descriptor table, maps FDs to files, read, loads file data into RAM only when needed, close, removes FD from the table, freeing the space. This is exactly how OSS handle file input output efficiently. I think this one is better. Okay, now what do I want to do now? Let's see what is the file descriptor now. It is still 14, even though I don't have the file. If if I don't have a file uh, whose name I gave in gave to the open at instruction, will I still get a file descriptor? Because I am getting a file descriptor. No, if the file does not exist and you call open at with the read only, the file descriptor will fail and return a val will not return a valid file descriptor. Instead, it will return a negative error code in the zeroth register. What happens if the file doesn't exist? When you call openat with a file name that does not exist, the kernel cannot read and file descriptor. Instead, zero will contain a negative error number, usually minus no such file or directory. No ent or minus 13 e access permission denied if you don't have access. Checking if openat succeeded. Compare zero, check if zero is negative. Oh, if negative, jump to error handling with the file descriptor. Okay. Uh, Now let's see handling missing files. If you want to create the file, if it doesn't exist, you need to use create. Okay, I can create a file actually, but why am I not getting an error when I'm reading a file that does not exist? I'm loading, I'm providing the arguments correctly. In the zeroth register, I have to provide -100, which is specifies the current directory. And then in the first, I have to provide the file name, which I get by first getting the page address, uh, and then adding the page offset to it. And then in the second and the third register, I give the value 0, which is also correct, it seems. And then I do a syscall. Yeah, and then I return with the file descriptor in the zeroth address, in the zeroth register. Hmm. Mhm. I just return here. Let's do this. Maybe. I don't know. Okay. I'm still getting a file descriptor which is not negative. But why am I getting that? Ask is name is here. Ah shit. Yep. Um File name dot txt. I'm sure I don't have that file name anywhere in my system. Let's see, do I still getting 14 as the file descriptor, which is not negative. Why am I getting that? Let's try to print it. Print the file descriptor using the printf function. If d as dot as keys as keys. The fd is percent d and then new line. So after this, I want to call the printf function. For that, in the zeroth register, I give 0 move. Oh shit. But I also want to give the file descriptor onto the stack. Okay. Str store the contents of the zeroth register onto the stack. That's good. Just store it onto the stack. Yeah, just store it. Uh, we get some space first, get 8 bytes of space, pre-increment, and then store it onto the stack. First, update the value of the stack to get 8 more bytes, and then store the value in the 0th register onto the stack. Then move in the 0th register the value 0, which means the standard output. And then I want to get the FD strings address in the first register, which is just um, move in the first register. Nope, not move. Get the add page address in the first register of FD page, and then add the offset page offset. And is there something else? Yep, there is. In the 16th register, I have to get it. Why am I being stupid? Um, I want to call printf, right? So for printf, the file descriptor, the file goes, the address of the string goes in the 0th register, and then I can just call printf. Let's see, clang it, and fd referenced from main. Fs, I messed up. I used fs here, but the thing there is fd. Okay, clang chapter 4 out. Nope. Yes, and dot slash out. Bus error. Bus error. Bus error. What is a bus error? Is it because of this? Store the file descriptor onto the stack, and then in the 0th register, I get the address of the string I want to print. So I have both the arguments for the printf function, and then I just return after calling the printf function. Okay, the file descriptor is 14, but why did I now not return? Did the return thing here? Is it because I didn't save the stack pointer? The stack pointer. All right, all right, all right. File descriptor seems to be 14. It's taking too long to write this simple, small program. Let's see the answer. We are get so what is the problem that we are facing? Even though we don't have file named file name not txt anywhere on our system, our sys call for opening a file is still going through. Some art is still going through, and we are getting a file descriptor for a file that does not exist. Input and read only. Write the assembly code equivalent to this using system call instruction. Let's read the question once again. The C library provides the openat function, which is documented in section 2 of the Linux manual pages. This function is a very small wrapper to allow C programmers to access the openat system call. Openat is a system call. We can use this function in C to access that syscall. Assembly programmers can access the system call directly. In ARM64 Linux, the system call number for openat is 56. what is the one that I'm using? 56. Is 56. The Linux system calls can be found on a Linux system. In this file, we can see the system calls. Okay. Write the ARM64 instruction and directives necessary to make a system call to open a file named input.txt for reading without using the C standard library. In other words, write the assembly equivalent to this using the svc instruction. Well, we have written the equivalent for that. We have made a system call. I think we can move on after this because they will explain more in more detail later in the book how system calls work. And yeah, that was all that we had to do. We were doing much more than what I was asked. You're reading the file and then closing the file. That is crazy, yo. Now we can begin the chapter 5. Yep. And let's see what is in the chapter 5. Chapter 5 is structured programming. It has sequences, selection, iteration, subroutines, which are functions, aggregated data types, and then chapter summary. And exercises, of course, 5 pages of exercises. So we are at page number 113. How much long can we go? I think we can complete sequencing, of course, and we will see about selection. 127 means we can complete sequencing. It is just a single paragraph. Uh, about selection, we will see if we will do it or not. Let's move on. We will at least study for 2 hours. Before IBM released Fortran in 1957, Fortran is pretty old. Almost all programming was done in assembly language. Part of the reason for this is that nobody knew how to design a good high-level language, nor did they know how to write a compiler to generate efficient code. Early attempts at high-level languages resulted in languages that were not well structured, difficult to read, and difficult to debug. The first release of Fortran was not a particularly elegant language by today's standards, but it did generate efficient machine code. In the 1960s, a new paradigm for designing high-level languages emerged. This new paradigm emphasized grouping program statements into blocks of code that execute from beginning to end. These basic blocks have only one entry point and one exit point. Control of which blocks are executed and in what order is accomplished with highly structured flow control statements. The structured program theorem, okay, provides the theoretical basis of structured programming. This is called structured programming, where we have different blocks of code which can be executed whenever we want, and the order and whether a block should be executed or not depends. We can specify it is accomplished with a highly structured flow control statements. Okay, it states that there are 3 ways of combining blocks, of combining basic blocks: sequencing, selection, and iteration. These 3 mechanisms are sufficient to express any computable function. It has been proven that all programs can be written using only basic blocks: the pre-test loop and if then else structure. Pre-test loop, test, and if it is true, then loop, and if it is not, then get out of the loop. And if then else structure. Although most high-level languages provide additional flow control statements for convenience of the programmer, they are just syntactical sugar. Other structured programming concepts include well-formed functions and procedures, step-by-step reference, and pass-by value, separate compilation, and information binding hiding. Okay. These structured programming languages enabled programmers to become much more productive, well written programs that adhere to structured Programming principles are much easier to write and understand, debug, and maintain. Most successful high-level languages are designed to enforce or at least facilitate good programming techniques. This is not generally true for assembly language. The burden of writing well-structured code lies with the programmer and not the language. The best assembly programmers rely heavily on structured programming concepts. Failure to do so results in the code that contains unnecessary branch instructions and, in the worst cases, results in something called a spaghetti code. Consider a code listing where a line has been drawn from each branch instruction to its destination. Right? We can make spaghetti code somehow. Then consider a code listing where a line has been drawn from each branch instruction to its destination. If the result looks like someone spilled a plate of spaghetti on the page, then listing is spaghetti code. If a program is spaghetti code, then the flow of control is difficult to follow. Spaghetti code is much more likely to have bugs and is extremely difficult to debug. If the flow of control is too complex for the programmer to follow, then it cannot be adequately debugged. It is the responsibility of the assembly language programmer, to write code that uses a block structured approach. Adhere to the structured programming principles results Adherence to the structured programming principles results in code that has much higher probability of working correctly. Also, well-written code has fewer branch statements. Therefore, the ratio of data processing statements versus branch statements is higher. High data processing density results in high throughput of data. In other words, writing code in a structured manner leads to high efficiency. Okay, so we want to reduce the number of branch instructions because that gives a good structure to the program. And we can, instead of just branching from one block to another, we can actually increase the amount of time we are spending on doing some calculation on the computer instead of just branching from one place to another. We can create good blocks and then jump between them only when necessary. And the blocks can help to reduce the amount of times we want to use the branch. Sequencing. Sequencing simply means executing statements or instructions in a linear sequence. When a statement n is completed, statement n plus 1 will be executed next. Uninterrupted sequences of statements from form basic blocks. Basic blocks have exactly one entry point and one exit point. Okay. Control flow is used to select which basic block should be executed next. Sequencing means executing one statement or instruction in a linear sequence, one after the another. That makes sense. Now, selection. The first control structure that we will examine is the basic selection construct. Shit, my absolute bad. That is horrible. I am a bad person. It seems. The laptop is running out of battery. Now it is not running out of battery. Well, it is running out of battery. Shit, I am a horrible person. Now, the first control structure that we will examine is the basic selection construct. It is called selection because it selects only one of two or possibly more blocks of code to execute based on some condition. In this most general form, the condition could be computed in a variety of ways, but most commonly it is the result of some comparison operation or the result of evaluating a Boolean expression. If then statement. The most important of selection. Shit. Yes. If then statement. The most important of selection is the if statement, listing 5.1, this one above. If this, then execute this block. 5.1 demonstrates a simple if statement in C. Listing 5.2 shows the AArch64 assembly translation. The first label is for clarity to show where the if statement begins, and the second label end if is in shows AArch64. If compare this and this, if branch link LT, what is LT? Shit, how can I not, how do I not know what BLT means? Branch and LT, less than. If the contents of x0 are less than the contents of x1, then branch here. Yes, otherwise just execute the if statement body. It shows the AArch64 assembly translation. The first label is for clarity to show where the if statement begins, and the second label end if is the end of the if state of the if statement. The condition in assembly is reversed from C. The C code checks if x0 and this to know if the if statement should be taken. In R64, the opposite check is used with the instruction BLT, branch if less than the x less than y, then the if statement is not executed. Instead, control branches past the if statement. Now this if then else statement. Most high level language is provide an extension to the basic if statement, which allows the programmer to select one or two possible blocks of choice to execute. The same behavior can be achieved by using two sequential if statements with logically opposite tests. However, the if then is else construct results in code that is more efficient as well as easier to read, understand, and debug. If then else statements using branch instructions. Okay, listing 5.3, which is here. Static. We have three integers, A, B, and C. If this, then do this, else do this. Okay, now branch listing 5.3 shows a typical if then else statement in C. Listing 5.4 shows the ARCH64 code equivalent using the branch instruction. Note that this method requires a conditional branch. Right? We have the address of A in 0 and the address of B in the first register, and we load the values in the 0th and the first register now. If this does the comparison of 0 and 1. Now, if greater GE is greater, right? Yep, greater or equal to. If the contents of 0, which is A, is greater than equal to the contents of the first register, which is B, then I go to else. That is, I do this. And then after that, if it is not, then I know that this is greater than this. Therefore, I move a value 1 to 0, and then I branch to end if. Or if it is actually greater, then I move here. I move the value 0 to 0, and then I end if. And end if just gets the address of x into 1 and stores the value of 0 into the address that is in 1. That is okay, acceptable. Note this that this method requires a conditional branch, an unconditional branch, and two labels. This is the most common method of writing the bodies of the then and else selection constructs. using conditional branch selection. Branching is not the only way to write an if statement. AArch64 selection instructions that are able to choose between two source registers based has selection instructions that are able to choose between two source registers based on a condition. These instructions can also optionally increment, set, or negate. Conditional set, increment, or negate conditionally. Listing 5.5. This shows the thing. Okay, we get the address of A and B and store A and B into 0 and 1 registers, and then we compare 0 and 1. And now we do set, conditionally set 0 to 1 if less than. And okay, what this instruction does is it checks for less than, which was which the less than state in the P state register, the flags which were updated by this instruction. And after checking it, if this is less than this, then 0 gets 1, and if if it is not less than this, then 0 is set to 1, to 0 actually. Okay, listing 5.5 shows the AArch64 code equivalent to listing 5.3 using conditional operations. Section 5.4.2110 covers the 11 conditional branch selection instructions in AArch64. While they cannot always be used to replace branch-based if statements, in certain examples, such as listing 5.4, they can be used to accomplish the same task without using any branch instructions. They can be used to accomplish the same task without using any branch instructions. In this and similar cases, the code is more efficient than using a branch. Okay, because we are not updating the program counter in them. Okay, complex selection in C. We have three numbers and four long numbers. What are we doing? If A is less than B and A is also less than C, then we put x equals A. Else we know that at least A is less than at least one of them. We know that A is not the smallest. A is either B is the smallest or C is the smallest. Now, if B is the smallest, then I put x equal to B, and if not, then we put x equal to C, and then we return complex selection. Okay. Uh, yo, Technoblade. Yeah, complex selection, we got time. More complex selection structures should be written with care. Okay. Listing 5.6 shows a fragment of C code which compares the variables A, B, and C and sets the X variable to the least of the three values. In C, Boolean expressions use short circuit equivalent. In C, Boolean expressions use short circuit equivalent. For example, consider the Boolean and operation in the expression this. If the first sub-expression evaluates to false, then the truth value of the complete expression can be immediately determined to be false. So the second sub-expression is not evaluated. This usually results in the compiler generating very efficient assembly code. Good programmers can take advantage of short circuiting by checking array bounds early in a Boolean expression and accessing array elements later in the expression. For example, the expression this file less than 15, check if array I is less than 0. Make sure that the index I is less than 15 before attempting to access the array. If the index is greater than 14, the array access will not take place. Okay, that makes sense. This prevents the program from attempting to access the 16th element on an array that has only 15 elements. That makes sense. Listing 5.7 shows an Arch 64. This is the equivalent for the code that we saw above. Okay, this is the equivalent. We have a main function. We store the frame pointer and the link register onto the stack, and we have, okay, we have quite a few things. We have a y variable which has 8 bytes. Then we have a variable which is 64 bytes long, and this is the value for a, this is the value for b, this is the value for c. Now we get the addresses of a, b, and c, and then we load a, b, and c into the 0 first and second register, and then in the if we compare 0 and 1. Now if a is greater than or equal to b, then I go to else if, where I compare b and c, because now at this point here I know that a is not the smallest. I compare 0 and 1. Now conditionally update the 0th register with 1 or 2 if less than. That is, if 1 is less than 2, then I store the value 1, and if that is not true, then I store the value of the second register into the 0th register. And then I end if by, how do I end if? I end if by getting the address of y into the ninth register, then storing the value of the 0th register into the ninth register, and then I return 0, move 0 into the 0th register, then load the stack point, the pointers, frame pointer, and the link register back from the stack, and then I return. Okay, and here, but now if a is not greater than b, then I know that b is greater. Now I want to check a and c, compare 0 and 2, and then go to else if. Else if is this, if if greater than or equal to, if a is greater than or equal to b, a is greater than or equal to c, then then I go here. Otherwise otherwise if a is not greater than c, and I also know that a is not greater than b, then I can just end, because the 0th register already has the value of a, which is the lowest now. But if it is not, then either a is the greatest or c is the greatest. And if at this point I know, when I'm in this instruction, I know that b is not the greatest, is not the smallest, because b is greater than a. So when I'm here, I either the answer is 0 or 2, that is a or c. And then if greater than, if a is greater than that, if a is greater than c, therefore the answer would be c. I go to the else if statement, else if, which compares b and c and updates the 0th register. Well, now I know that b is greater than a, and a is greater than c, therefore b will also be greater than c, therefore this instruction will result in a 0th register being updated with the value of the of c, whatever is the value of c, which is this. Okay, so this works. listing 5.7 shows an AArch64 assembly code fragment which is equivalent to listing 5.6. In this code fragment, x0 is used to store a temporary variable for the variable y, and the value is only stored to memory once at the end of the fragment of the code. The first if statement is implemented using branch instructions. Its comparison is the first if statement is implemented using branch instructions. Yes, its comparison is performed on line 17 of listing 5.7. If the comparison evaluates to false, then it immediately branches off to else if block. But if the first comparison evaluates to true, then it performs the second comparison in the if statement. Again, if the comparison evaluates to false, wait. Here we are. The first if statement is implemented using branch instructions. Its comparison is performed on line 17 of listing 5.7. Line 17 here. This this thing. If the comparison evaluates to false, then it immediately branches to else if. But if the first comparison evaluates to true, then it performs the second comparison and if in the if statement. Okay, it if that comparison evaluates to false, then it branches to the else if statement block. If both comparisons evaluate to true, then it executes x0 equals to 8 and then branches to end if label. In this case, x0 is already set to a, so it just branches to end if. That makes sense. Now, the if statement on line 9, that is this. The if statement on line 9, this on line 9 of listing 5.6 is implemented using conditional selection. The comparison is performed on line 23. Oh, in the C in listing 5.6. Okay. In comparison on line 23, the equivalent code is there. This listing 5.723 is this. This is just a label. This is the actual comparison. Line 24 contains the instruction that conditionally selects the result value. 24, which is this. Now, unconditional loop in AArch64 assembly. Unconditional loop. Okay, we have a string hello world. Then in the text section, we have a function main, and which is also global. That is, it can be accessed from outside this file. And then in the main, we have a loop, which first gets the address into the 0th register. For this, then it branches off to the printf function, and then it branches off to the loop. Fuck, this is just a non-stop loop. This will keep on going, infinite loop. Note that the number of comparisons that execute will always be minimized, and the number of branches has also been minimized. The only way that line 23 can be reached is if one of the first two comparisons evaluates to false. The program fragment will always reach line 29 and a value will be stored in X. Thus, the AArch64 assembly code fragment in listing 5.7 can be considered to be a block of code with exactly one entry point and one exit point. Yes, because it will always exit at this label, and it will always enter from here, this thing. Now, when writing nested selection structures, it is important to maintain a block structure, even if the bodies of the blocks consists of. When writing a nested selection structure, it is important to maintain a block structure, even if the bodies of the block consists of only a single instruction. It is often very helpful to write the algorithm in a pseudocode or a high-level language such as C or Java before converting it to assembly. Prolific commenting of the code is also strongly encouraged. Prolific commenting. Okay, so we have done that part. That much. What is the time? We still have 10 more minutes. We can do the iteration. How long is the iteration thing? It is not long. Yes, we got this. We got the iteration part figured out. Iteration is what? Iteration involves the transfer of control from a statement in sequence to a previous statement in the sequence. That makes sense. The simplest type of iteration is the unconditional loop. This is the unconditional loop, also known as the infinite loop. This type of loop may be used in programs or tasks that should continue running indefinitely. Listing 5.6 shows an AArch64 assembly fragment containing an unconditional loop. Few high-level languages provide a true unconditional loop, but the high-level programmer can achieve a similar effect by using a conditional loop and specifying a condition that always evaluates to true. Pre-test loop. We first do a test, and if it is true, then we loop, and if it is not, then we do not loop. A pre-test loop is a loop in which a test is performed before the block of instructions performing the loop body is executed. If the test evaluates to true, then the loop body is executed. The last instruction in the loop body is branch back to the beginning of the text, to the beginning of the test. If the test evaluates to false, then the instruction branches to the first instruction following the loop body. All structured programming languages have a free pre-test loop construct. For example, in C, the pre-test loop is called a while loop. In assembly, a pre-test loop is constructed very similarly to an if-else statement. The only difference is that it includes an additional branch instruction at the end of the sequence for instruction that forms the body. Listing 5.10 shows a pre-test loop in AArch64. 10. This is pre-test in C, while do this, and this is pre-test in assembly. Compare this, and if x0 is less than this, then go to done. And at the end of the loop, if it is false, that is x1 is x0 zeroth register is greater than or equal to the contents of the first register, then execute the code, and at the end of the code, go back to the test where you started doing whatever the heck you're doing. In a post-test loop, the test is performed after the loop body is executed. If the test evaluates to true, post-test, first we execute the block and then we test our condition, and if it is true, then we go back to the start of the block. And if it is false, we continue moving ahead of the loop. We execute the instruction that is after the loop. In a post-test loop, the test is performed after the loop body is executed. If the test evaluates to true, then execution branches to the first instruction in the loop body. Otherwise, the execution continues sequentially. Most structured programmings have a post-test loop. For example, in C, we have do while loop. Yep. Listing 5.11 shows a 5.11. Do this execute all this first, then check if it is this thing is true, and if this thing is true, start executing this again. Okay, now in a post test loop, the test is okay. Yes, 15.5.11 shows a do while loop in C. Yes, and listing 5.12 shows the post test loop in assembly. We just do our thing and we compare, and if it is greater than, then we do this again, and we still do the test again, and if it is true what we are checking for, then we do it again and again and again infinitely till the condition shows its true colors and turns to false, becomes the Judith. A post-test loop is more efficient than a pre-test loop because it will always perform the loop test one time less than pre-test loop and has one fewer branch instruction. When the test fails, the post-test loop can exit immediately. A pre-test loop must first branch up to the beginning and then back down to the end. When the programmer can guarantee that the loop body must always be executed at least once, a post-test loop is obviously the better choice. That makes sense. Even if the loop body is not guaranteed to execute at all once, in all cases, the post-test loop can provide a slightly better performance. In order to take advantage of this efficiency, pre-test loops can be turned into post-test by adding one check before the pre-test loop begins. This is commonly referred to as a guarded loop. The guarded loop is shown in figure 5.3. Compare before, and if this is true, then end loop, or if it is not, then just start executing the post-test loop. Now, we have here, what do we have here? We have a for loop. Many structured programming languages, that is, structured means the code is divided into blocks, and blocks contain uh, statements, and these blocks of statements are executed at different times, and we can tell if we want to execute a block and the order in which we want to execute these blocks using the structure of the language that the language provides, the interface of the language. Now, many structured programming languages have a for loop construct, which is a type of counting loop. The for loop is not essential and is only included as a matter of syntactical convenience. In some cases, a for loop is easier to write and understand than equivalent pre-test or post-test loop. Okay, a for loop is just syntactical convenience sugar. However, with the addition of an if-else statement, any loop can be implemented as a pre-test loop. The following section shows how loops can be converted from one form to another. Listening is for this, print this from I 0 till I is less than 10, that is till 9. And when I becomes 10, the program will exit. How is this done? Oh, now listing 5.15, loop rewritten in a pre-test loop in C. Uh, this I equals this while check the condition, print this, and every time increment 1, I by 1. For loop in C and for loop rewritten as a pre-test loop in C. That makes sense. Okay, in do most assembly languages do not have a for loop. However, any for loop can be converted to a pre-test loop. Any for loop can be converted to a pre-test loop, just the same way we did here. We converted this pre-test loop, this for loop, into a pre-test loop here. Okay. Listing 5.14 shows a simple C program for loop with a for loop. The program prints hello world 10 times, appending an integer to the end of each line. Oh, we have this hello world hyphen 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In order to write an equivalent program in assembly, the programmer must first rewrite. Okay, let us write this pre-test loop in assembly ourselves. It re and iterate hello world dot s. Now in here, first in the data section, we will define a string which will store as keys for hello. world hyphen d print new line. Okay, and then in the dot text section we will tell that we have a global label called main, and we want to align at 4 bytes. And then in the main we have, we don't have to mess up with the stack pointer, we are not changing it, so I will not even store the stack pointer. First I want to get the address of the thing that I want to store in the zeroth address, the string in the zeroth place, but I will mess up. I want to access the stack pointer because I am using the printf statement, the printf instruction. So store pair of 29 and the 30th register in the stack pointer by giving them new 16 bytes and pre-increment them. Now, what do I? Okay, first I will get the address in the 0th register. I will get the address of the page of strings page, and then add the offset to the 0th register string page offset, right? And I can also move this to the 9th register so that when the 0th register is overwritten by the printf function, I do not have to get the address of the label from the start by getting the page address and then adding the offset. So now I have the address that I want, and let's also initialize move into the 10th register 0, which will do our I thing that we do. So this is for all of this is for initializing stuff. Now here we tell, we check, right? Um, we want this to be pre-increment, pre-test. So we compare the contents of the 10th register, which is our counter, with the value 10, right? And branch greater than or equal to. If the contents of the 10th register are greater than or equal to the value 10, then we branch to end loop. Okay, otherwise we have loop here. Loop contains, starts a loop. And what does the loop do? It uh, gets, shit, what was I doing there? Yep, it first loads into the 0th register, move into x0, the value in x9. Now I have the address in the 0th register. Now I want to store the integer in the at the top of the stack. For that, store the contents of 10th register, the top of the stack, and then call the printf function. Now, after calling the printf function, I want to increment the contents of extend, that is, add and store to the 10th register value 1, and yeah, that should do it. And at the end, what do I do? I branch unconditionally to the loop, and here I should have end loop, which will, what will this do? This will just return. Now I want the lang iteration word. Okay, dot slash a dot out hello world, and then nothing. Terrible. Okay, there seems to be some mistake. Oh, well, this is not the cause of the mistake, but I spotted a problem here. I load pair of 29th and 30th register back into the stack. Yep, I think I should have get more space when I'm storing. Yep, here when I'm storing it. So for that, I will just do add to the stack pointer, store to the stack pointer. I'm directly working with the stack pointer. That is crazy. 8 bytes. And then at the end, I subtract and store in the stack pointer 8. Well, I am just so stupid. I adding to stack pointer means um, reducing the size of the stack, and subtracting to the stack pointer means increasing the size of the stack. That is just the way it works here. So what am I doing here? Oh, I have to check this. Uh, in the loop, here dot out and bus error. Let's see. It is due to the stack pointer thing I did here. Subtracting 8 from the stack pointer. That is most probably the reason. Let's see. I will just go to the washroom for a minute. Come back in a minute. Just wait. Yep. Me back and me drink water. Yes. Write a program to print hello world multiple times. Okay. I am I'm getting a bus error now. Why is that? I am subtracting from stack pointer the value 8 to get new 8 bytes. And then what am I doing? I am comparing the value in the 10th register with 10. And if it is, if the value of the 10th register is greater than or equal to 10, I am ending the loop. Otherwise, what am I doing? In the 0th register, I am getting the address for the string, and then I am storing the value in the 10th register at the top of the stack, and then I am calling printf function. Yes, I am calling the printf function with these values, the string and the number that will be printed on the screen. And then I add 1 to the 10th register contents. And then I go to the top of the loop after incrementing 10 by 1. This should be executed 10 times, starting from 1 to 9. And when 10 becomes the contents of the 10th register become equal to 10, I will do end loop and add 8 to the stack pointer to deallocate the memory which I got um, here by subtracting 8, and then I load back the values of 29th and the 30th register from the stack, and then I return. And why is this causing an error? So maybe I should do this dot slash out. Okay, there is seems to be a problem. I don't know what the problem is. The problem is because of the stack pointer. But why is this a problem? I'm just subtracting 8 from the stack pointer. This should not cause a problem. I am only increasing the size of the stack by subtracting some value. Bus error. That is, I am storing or loading more than I can. Is that it? Mm, mm. I'm adding 8 here to the stack pointer. Subtracting 8. Is there another way I can provide a string? Okay, let's remove this part and this part and this part, and instead of doing this, we will just try to print hello world itself. Okay, we will try to print hello world 10 times and it did not print 10 times. Okay, why is that? I am going to the top of the loop again. Here I compare this and that, and then I move to that. This should not cause any problem. This actually should not cause any problem, but there are problems being caused. Is the 10th register being overwritten by the printf function? I don't know. I couldn't say. Hmm. I'm looping back to the top. And then there I'm comparing, and then I'm getting ready for the printf, and then calling the printf, and then add incrementing. I can remove this. I'm not playing with the stack anymore. And I'm moving before executing the loop. I'm moving the contents of x0th register into the 9th register, and I am also initializing the 10th register. How does this work? Mm, what is being messed up? Hello world is being printed only once. Ah shit, I closed the terminal. Simply an iteration, yes. What am I doing wrong here? What am I missing here? This should return ENDLOOP. Yep, there's no mistake in spelling. It seems. Yep. No typo. Then I am also moving, getting the address to be printed by the printf function, and also incrementing the 10th register. The only source of problem seems like the printf function is overwriting the contents of the 10th register. So let me use some other register. Let's say, I don't know, the register, I don't know, 15 maybe, the 15th register. Instead of 10, I can use the 15th register. Right, yeah, wait. Let's see. Lang iteration and out, dot slash out. Still, I am missing somewhere. This has to be a very stupid mistake I'm doing. Let's see. Let's see. What is wrong with me? There. Okay. Your code has a few issues, mostly related to calling convention and missing external dependencies. Printf is not defined or imported. Why do I have to uh, define printf? It is a part of the C standard library. The printf function is a part of the C standard library. You need to declare it as an external function using .extern printf on macOS or .extern on Linux. Incorrect calling convention for printf on macOS. The first argument format string should be in 0th register, but you need also to set up x1 and x2 depending on the argument. In your case, printf requires a format string, but you are passing the string directly without a format specifier. Okay, missing main return. The main also has to return the mark. Okay, let's see what you do in your code. Get the address into the 0th register, move the address to the 15th register, okay, and then in the loop, compare it with 10, and if it is greater than, then end the loop, or then call the printf function directly. I can just do that. Okay, add 1 to the 15th register. Will this not, the printf function will not overwrite? Okay, let's do what ChatGPT says, even though it is not making sense. The segfault. Yep, because of this line. The x0 was updated by printf to contain the return value. So when I called printf without storing the address in the 0th register, I got an segmentation fault because I was trying to access something I should not have. I think the 9th register is being overwritten by printf function. So do I have to access memory again and again to get the address back? So do I have to store the address onto the stack? That is pretty stupid. Store pair x29 and x30 onto the stack and pre-increment it with 16 to get some free space, and then instead of doing this, do store store the value of the zeroth register onto the stack after pre-incrementing it with 8, right? And at the start, instead of getting the address from the ninth register, uh, load into the zeroth register whatever is the value at the top of the stack. Then in the end, first of all, add to the stack pointer the value 8 so that I lose the 8 bytes that I gave to the stack here on this line, and then load pair the 29th and the 30th register from the stack, and then add 16 to it. Bus. This is messed up. Even ChatGPT can't tell me what is wrong with this. See, what can Claude tell me? Claude Shannon. Uh, what is wrong with this code written in AArch64 assembly for Mac OS M1 chip? High Q. And due to high demand, Claude 3.5 Sonnet is temporarily unavailable for free clients. Claude 3.5 Haiku is faster but may provide less detailed responses. Where they are saying that this is store this save pointer and move the stack pointer in the to set up. So I set up the frame pointer, then I initialize control in the 19th register. Use call save. Okay, use the 19th instead of the 15th register. Okay, then loop, compare the counter. Okay, and if it's greater than, then end loop, else get the add. Okay, I'm getting the address every time, and then calling printf and then adding one. Okay, so according to Claude, I should not do this. Instead of this, I can just do this, and I don't have to manipulate the stack at all. And here, instead of 15, I should use the 19th register, and all set. Let's see if it works. I, let's function yet, but I did not end the program. I did not end. And I also want to print the number. So I also want to print the number like this and give it as an argument to the stack pointer. And so load the value, the content of the 19th register at the place of the stack pointer, and yes, I want to have 8 bytes to store that, and that has to be pre-increment. And at the end, I can add to the stack pointer and store to the stack pointer the value 8, const 8, the constant 8. And okay, here I am getting that. And I have to not load but store str, and here also I store the contents of the 19th register on. just directly on the stack. Error? Yep, error. Why am I getting an error? Let's just go bonkers and use 20 bytes of free storage. Free, absolutely free. But subtract from stack pointer the values 20 and store it here like that. Let's see if that works. Better. Hmm. Why am I getting a bus error? It is always due to the stack. The stack is messing up. Oh, well, I am stupid, right? Nope, not the 29th, the 19th register, the contents of the 19th register. Let's see. Bus error. Why am I getting a bus error? Why am I getting a bus error? Why am I getting a bus error? The stack pointer points to the top of the stack, and here I am subtracting 20. That is, I am getting 20 bytes free from the stack, and then at the end, I am adding 20 bytes to get back where I started. Mhm, 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 mhm. Um, Maybe I can move into the first register, the contents of the 19th register, get the value, to give the value to the printf function, but that is not how printf takes input on Mac OS. So, well, at least we got that part sorted out. But why am I not able to print? Now, the thing is, let's see, in the book, I have printed before, right? I have done the printing part before a lot of times. Printf segmentation fault, shit, that is crazy. And in chapter 3, we have worked for uh, I haven't used printf function in chapter 3. Okay, in chapter 4, I must have used printf. Yep, there we go. And then here, and the string. Okay, where is the string? String is this. Nope, this is the string for the function below it. Yep, this string also has a %d sign. That is I have to provide a number to it to be printed. Now, how do I do that? I get the address, store the thing at the top of the stack pointer, then I do this, then I do this, and then I load back the pair and add 16 to it. So why heck is it not working here? Let's first store pair 29 and the 30th register onto the stack and add the 16 pre-increment, right? And then not do this, right? We'll not do that. And then all we will do is just load the pair Load the contents of 29th and the 30th register back from the stack. Yes, and here is comparison that is perfectly good. And then here is we are storing the value at the stack. Yes, perfectly good. Yep, yep. Storing the value on at the stack. Yep, yep, yep. This should actually work. Should actually work. Should actually work. This should actually work. And as function yet, yes. Oh, it is working now. It has been quite some time, 32 hours and 30 minutes long stream. Now, post increment convention, and then we are done. Yep. If the programmer can guarantee that the body of a for loop will always execute at least once, then the for loop can be converted to the equivalent post increment test loop. Post increment, we will be testing after that we have performed the instruction. This form of loop is more efficient because the program control variable is tested one time less than pre-increment loop. Also, a post-increment loop requires only one label and one conditional branch instruction, whereas a test increment requires two labels, a conditional branch and an unconditional branch. Okay, pre-test increment, pre-test. Here I have the string, the text section. I get stuff and I compare the contents of the fourth register with 10, and then if it is greater, then I go done, and if it is not, then I get the address of the string in the zeroth register. I move the contents of fourth into the first register, and then I call the printf and this. Okay, this assembly is quite different from the one I am writing because mine is on Mac M1 and this is for Linux, so the operating system is different. And yeah, the operating system is different. Since the loop in listing 5.14 always executes the body exactly 10 times, we know that the body will always execute at least once. Therefore, the loop can be converted to a post increment loop. Listing 5.17 shows the program rewritten as a post test so that it is easier to translate into assembly. Note that as in the previous example, the initialization of the loop variable has been moved to its own line before the do while loop, and the loop variable is modified on the last line of the loop body. Makes sense? This post-test version will produce the same output as the pre-test version. This is a straightforward conversion from one type of loop to an equivalent type. Listing 5.18 shows a straightforward translation of the post-test loop structure into AArch64 assembly. Here we load, we initialize the X register with 0, and then we get the address. We give the variable in the 0 in the first register as the parameter. We call the printf function, right? And then we add one increment, and then we compare. And if 4 is less than 10, then we loop back and do this again and again. And tomorrow we will start with the subroutines. Subroutines are functions. Yep, subroutines are just normal functions. And now that is it. 2 hours, 33 minutes of streaming.